In this video, I'm going to explain how we can solve heat equation or diffusion equation using Crank-Nicholson together with Thomas method. So here is the general form of a diffusion equation or heat equation. W is the dependent function, x and t are independent variables. So dw dt equals d squared w over dx squared. We learned in class that if you do discretization using central differencing on both sides, we get something like this. On the left side, we get wi comma j plus 1 minus wi comma j over del t. This is equal to everything on the right side now is going to be centered at j plus half. All right, so that is wi minus 1 comma j plus half minus 2wi comma j plus half plus wi plus 1 j plus half. So j plus half is fixed. Index over I varies from I minus 1 to I and then to I plus 1. And the whole thing divided by del x squared. If I multiply this equation through by del x squared, you're going to see that on the left side I get del x squared over del t times basically the left side equals the right side. Let's call this equation 1. Now, I'm going to rewrite all these j plus half variables in terms of average of variables expressed in j and j plus 1. That is to say, wi comma j plus half is equal to 1/2 of wi comma j plus 1 plus wi comma j. So this plus 1 is actually the index, is not the, it doesn't mean wi comma j plus 1. All right, so it's j plus 1 is the subindex. In the same fashion, we can say wi minus 1 on j plus half is equal to 1/2 of wi minus 1 comma j plus 1 plus wi minus 1j. So you can see that index over I does not change, but the index over j actually, if you take the average of the j indices, you get j plus half. So in the same way, you can expand wi plus 1 comma j plus half. Now, if you combine these three equations with equation 1, you can see that on the left side here, we get del x squared over del t times this thing, as I can have here. That is equal to, on the right side, all the j plus half variables now is the average, or become average of j plus 1 and j. So the first term is this plus that divided by 2. So there's a 2 looks like missing here. And then I comma j plus half plus I comma j divided by 2. Again, there's a 2 missing here. And then this divided by 2. So if I multiply the equation through by 2, then 2 on the right side is going to go away. And then you get an extra 2 up front on the left side. That's why I have a 2 here. All right? So this is after you combine equation 1 and 2. So now let's look at this equation and see what the unknowns are and what the knowns are. The unknowns are all the j plus 1 variable, and the j variables are all known. So we're going to move all the j plus 1 variable to the left and all j variables to the right. By doing so, you get something like this: negative wi minus 1 comma j plus 1 plus 2 times 1 plus del x squared over del t. So there's a typo here. This should be del t times wi comma j plus 1 minus wi plus 1 comma j plus 1. So all the j plus 1 variables are on the left. You can see that. And now all the j variables on the right. Okay? So now let's plug in j equals 0. So once we plug j equal to 0, then we get something like this. So basically you just look at this and plug j equals 0. You get negative I minus 1 comma 1. So the coefficient stays the same. This becomes I comma 1. This becomes I plus 1 comma 1. And then on the right side you get I minus 1 comma 0, I comma 0, and then this one is I plus 1, comma 0. So all the comma zeros on the right, comma 1s are on the left. So now let's substitute some of these variables. I'm going to substitute all the comma 1 variables, like this one, comma 1, comma 1, comma 1, all the comma 1 variables with u's, and all the comma 0 variables with v's. That is to say, w 0, comma 1, 1, comma 1, 2, comma 1, all the way to n plus 1, comma 1, become u0, u1, u2, all the way to un plus 1, and the w0, 0, 1, 0, 2, 0, and n plus 1, 0 becomes v's. Now I just want to emphasize that here we are discretizing actually our domain to n plus 2 points. So this is very important. N variables or n points are intermediate points from 1 to n and 2 boundary points. That is 0 and n plus 1. So total I have n plus 2 variables. But I can only write the heat equation for n points from 1 to n. I cannot write heat equation for the boundary points. For boundary points, I need boundary conditions, which we get to, I think, in the next movie. All right, so let's get back to the equation. Now I have this equation where still I is a variable. So now I can plug in I equal 1, 2, 3, all the way to n. Again, these are the intermediate points. That's why I starts from 1 to n. You cannot put I equals 0. You cannot put I equal n plus 1. All right? So let's put I equals 0. You can rewrite this equation using these new variables as negative u0 plus 2 times 1 plus del x squared over del t times u1 minus u2 equals v0 minus 2 times 1 minus del x squared over del t v1 plus v2. And that is when I equals 1. If you put I equals 2, basically you're going to increase all the sub-indices by 1. So this becomes minus u1, coefficient is the same. This becomes u2, this becomes u3, this becomes v1, v2, v3. If you plug in I equals 3 in there, you get negative u2, so indices again go up by 1. u2 become u3, u3 become u4, v1 become v2, v2 become v3, v3 become v4, and so forth. And the last one is when you plug in I equal n. So these are the equations that we just have using Crank-Nicholson. Now we need another method to solve this system. So you see that I have a system of equation. On the left I have u0 to un plus 1, and on the left side, on the right side, I have all known variables. So in the next video, I'm going to show you how we can use Thomas method to solve the system using the boundary conditions that we have to apply. Thank you so much for watching.